Triatlas has company. Astronomers detect an almost identical comet, V1. That's what set off alarm bells at observatories around the world when the first measurements confirmed that a second object with strikingly similar characteristics was crossing the space near the solar system. Nobody expected something like this to appear right now, in the middle of the critical phase of tracking 3I Atlas, but the images left no room for doubt. A new visitor was entering the scene, and its initial behavior showed a coincidence that couldn't be ignored. What seemed like a simple green dot on the automatic record ended up revealing a pattern that had only been observed in objects originating outside the solar system. The anomalous speed, the hyperbolic trajectory, and the type of emissions detected in its coma instantly caught the attention of teams specializing in interstellar bodies. Each new reading reinforced the same conclusion: a perfectly ordinary comet. And the most surprising thing was that, despite being independent, its luminous composition and initial activity were almost a mirror image of 3I Atlas. Within hours, the scientific community began reorganizing priorities, redirecting telescopes, and extending observation shifts. Having even a single interstellar visitor was already a rare event. Having two with similar characteristics in the same period was completely unprecedented. And what these objects carry with them isn't just ice and dust, but real clues about the material that exists in remote regions of the galaxy. That's why this discovery immediately became one of the most important of the year. If you're watching this video, get ready because this finding is putting the world's leading telescopes to work. Before going into the deeper details, I want to invite you to like this video and tell me in the comments what city or country you're watching from. It's always amazing to see where people are joining us from when we talk about such extraordinary cosmic phenomena. What we have today isn't just a simple update on the Atlas 3I, but a situation that took even the most experienced teams by surprise, for weeks. The follow-up observations of 3I Atlas were already generating a considerable amount of information, but the discovery of B1 reshuffled all priorities. Astronomers didn't expect to find another object with the same spectral signature and dynamic behavior as an active interstellar visitor, but that's exactly what happened. Initial confirmation came from a careful comparison of images from different observatories, analyzing not only the characteristic color of the coma, but also how sunlight excited certain molecules. This is crucial for understanding where this object might have come from and whether it truly has a similar nature to 3I Atlas. For now, what they know is that both comets show signs of origin beyond the Oort cloud, meaning they weren't born in the common regions of the solar system. This coincidence makes the event a unique opportunity to study extraterrestrial material in two distinct, yet remarkably similar, versions. And from here on out, every part of the analysis matters, because each new piece of data helps reconstruct what these two comets represent for modern astronomy. The confirmation of object V1 began with something that, for most observatories, would have gone unnoticed as a simple flash in an automated tracking sequence. However, at facilities specializing in fast-moving objects, any trace showing anomalous acceleration triggers an immediate review. And that's exactly what happened. The initial recording showed a faint point of brightness that appeared to be moving slightly faster than conventional comets visible in the same region of the sky. These types of signals are usually reviewed several times with different filters to rule out digital interference or satellites crossing the image. It was in this detailed comparison that something noteworthy was noticed. The object's preliminary spectrum did not match the behavior of traditional comets. The reason was simple. The light it emitted contained an atypical proportion of emissions associated with excited molecules, which are not usually seen with such intensity in comets born within the solar system. By making the first precise measurement of its trajectory, the teams detected that the angle at which B1 was entering did not correspond to common orbits linked to the Oort cloud or to known families of periodic comets. Instead of a smooth curve, its path showed an open shape typical of hyperbolic trajectories, the type exhibited only by objects not gravitationally bound to the Sun. This immediately placed B1 in the category of a possible interstellar visitor, something extremely rare, given that only a handful of bodies with this profile have been observed throughout history. The relationship between B1's relative velocity and the Sun's gravitational influence reinforced this possibility, as the object showed no signs of deceleration consistent with bodies originating in the inner or middle regions of the system. As the measurements accumulated, an even bigger surprise emerged. The detected emissions had a chemical signature very similar to that of Atlas 1I. This didn't mean they were identical, but they did share certain unusual patterns in their comas, particularly in the way sunlight excited diatomic carbon molecules. That green glow that has generated so much debate regarding Atlas 3I was also present in B1, although in a slightly smaller proportion in the initial observations. This detail prompted scientists to directly compare both sets of data to analyze whether the match was mere coincidence or if there were deeper elements in common. Meanwhile, large aperture telescopes began focusing on the object to obtain high-resolution images. These new images revealed that B1 had a small nucleus surrounded by a compact coma with a trail of activity that varied according to its distance from the Sun. Although not as extended as that of 3 Atlas, the tail showed enough activity to rule out the possibility that it was an inert body or an interstellar rocky fragment. The interaction between solar radiation and the object's volatile compounds showed that B1 contained sublimating ice, a characteristic feature of active comets. Astronomers then began reviewing databases of objects discovered in recent months to check if B1 might have been recorded before without being correctly identified. However, nothing matched its speed or its initial position. This reinforced the conclusion that the object appeared almost unexpectedly in the instruments, possibly due to its small size or because its activity was too weak before it approached the Sun. This type of behavior is common in comets that come from extremely cold regions, where they remain dormant for millions of years until solar radiation awakens them as they approach the system. Another crucial point of analysis was the comparison between the velocity curve of B1 and that of 3 Atlas. Although the values were not identical, both showed similar patterns when fitted to models of interstellar objects. This led several specialists to consider the possibility that B1 could have been ejected in a way similar to the one that may have ejected 3I Atlas from its original system. Dynamic simulations of interstellar bodies show that it is entirely possible for multiple objects to be ejected from the same star system during gravitational perturbation events, such as the passage of a nearby star or interactions with forming giant planets. Even so, demonstrating a direct relationship between B1 and 3I Atlas will require much more precise data, especially complete spectral measurements that allow for the identification of the exact proportion of elements present. As the measurements continued, something caught the astronomers' attention. B1's luminosity was increasing faster than expected as it approached the Sun. This often occurs when certain volatile compounds begin to sublimate in greater quantities, revealing internal layers of the nucleus. Although this increase was not as dramatic as that recorded in 3I Atlas, it did suggest that the object possessed internal characteristics consistent with active comets originating from extremely cold regions. Analyzing these variations is fundamental for estimating not only the object's composition, but also its size, density, and degree of erosion. The international scientific community then began coordinating observations across different wavelengths. Infrared-sensitive telescopes sought to detect heat emitted by the nucleus, while optical instruments analyzed the scattering of light in the coma. These comparisons are essential to determine whether B1 possesses dust particles similar to those of 3 Atlas, or if its composition exhibits significant variations. Each of these observations, combined with the apparently hyperbolic trajectory, strengthened the classification of B1 as an object of external origin. With each new reading, one idea became clear: B1 was no ordinary comet, and its resemblance to 3 Atlas could not be ignored. Although critical details such as the exact proportion of sublimating gases and its actual size still needed to be confirmed, the similarities were enough to categorize it as one of the most significant discoveries of the year. The appearance of 2 potentially interstellar objects with such similar physical characteristics. This opened the door to an unprecedented number of comparative studies that could reveal valuable information about the formation of planetary systems in other regions of the galaxy. When scientific teams began to analyze B1's orbital dynamics in greater depth, one of the first elements that caught their attention was the way the object reacted to the Sun's gravitational influence. Unlike comets from the Oort cloud, which typically exhibit a gradual deceleration as they approach the inner regions of the solar system, B1 maintained an unusually high speed that did not match classical models. This characteristic aligns with what is expected of an interstellar object, since its orbital energy is not controlled by the Sun's gravitational constraints. This kinematic independence is one of the most reliable features for distinguishing a local body from one originating from outer regions of the galaxy. It is in these details that specialists found signals consistent with the behavior of 3I Atlas, whose trajectory has also been classified as hyperbolic, indicating that it will not return once it ventures back into deep space. As studies of its motion deepened, another aspect generated particular interest: the way in which B1's coma scattered sunlight. Initial analyses had already detected a strong presence of the green glow characteristic of diatomic carbon molecules, but it was in the more detailed comparison that deeper parallels emerged between B1 and comets 3 and Atlas. Both objects showed an emission pattern where the intensity of C2 increased as they approached the Sun, something common in active comets, but with a spectral distribution that is not typical of local bodies. This type of behavior is usually associated with materials that have not been processed for long periods in the inner regions of the solar system, suggesting that both B1 and 3I Atlas may have spent millions of years in extremely cold environments before beginning their current trajectories. The researchers then began to compare the evolution of activity between the two objects. 3I Atlas has shown dramatic variations in its luminosity, changes that have been interpreted as intense sublimation events or the release of surface fragments. In the case of B1, although the scale was smaller, the steady increase in its brightness confirmed that the object was not a passive rocky fragment, but a comet with volatile material, capable of being easily released when heated by solar radiation. This comparison established that even if B1 is smaller or less active, it shares very similar physical processes, which raises the possibility that both originated from environments where temperatures and chemical conditions favor the preservation of highly volatile compounds. As more data was obtained, an interesting issue arose concerning the orientation of the coma. Conventional comets typically exhibit an orientation influenced by the solar wind and the relationship between the nucleus's rotation and its distance from the sun. In B1, the coma showed a slight distortion that did not entirely match what was expected for a small and relatively young body. Something similar had already been observed in Atlas 3I, whose shape and directional activity suggested an irregular internal geometry or a highly localized emission source, although it cannot be stated that the two objects share an identical physical structure. The similarities between the gas emission patterns raised new questions about the types of materials present in Min2 and Sinton PC, their surfaces, and the thermal history they may have experienced during their interstellar journey. Another significant point was the study of the nucleus's albedo. Although it is difficult to measure the exact albedo without high-resolution observations, preliminary models indicated that B1 might have low reflectivity, a common characteristic in comets composed of dark, organic materials. This same pattern had been observed in Atlas 3I, strengthening the idea that both objects could be composed of similar compounds, possibly resulting from chemical processes in the protoplanetary disks of other stars. The importance of this coincidence lies in the fact that interstellar comets act as capsules that preserve ancient conditions and materials, offering a direct window into the chemical composition of regions of space that we will never be able to physically visit. As the analyses progressed, astronomers began to study the possibility that B1 was undergoing rotation that affected the distribution of its activity. This type of behavior is common in comets with irregular structures or fractures in their nuclei. Periodic variations in luminosity had already been detected in data from the 3I Atlas telescope and were interpreted as signs of rotation for B1. Although the variations were more subtle, the pattern suggested a similar process. This was noteworthy because it could indicate that both objects, despite their differences in size and activity, might have been shaped by similar dynamic environments before being ejected from their original systems. Meanwhile, telescopes sensitive to ultraviolet and infrared light provided new information about the object's internal composition. Ultraviolet observations revealed the presence of highly volatile molecules that are released at relatively low temperatures, which is consistent with the interpretation that B1 contains very unprocessed material. In the infrared, some instruments managed to record the thermal emission from the nucleus, although only to a limited extent due to its small size. However, even these partial data reinforce the idea that B1 shares certain thermal characteristics with 3I Atlas, particularly in the way its surface ice absorbs and releases energy. One of the most important debates among experts was whether this similarity could be considered evidence of a common origin. Although there is still no definitive answer, several elements support this possibility. Both objects show similar chemical signatures, compatible hyperbolic trajectories, and activity levels consistent with comets that have remained in extremely cold regions for long periods. Furthermore, gravitational ejection models suggest that a stellar system can release multiple objects simultaneously, especially during phases of orbital instability. However, to confirm this, comprehensive spectral measurements will be needed to accurately compare the proportion of the same compounds present in both bodies. For now, what is clear is that B1 represents a new opportunity to study interstellar processes with unprecedented depth. Having two objects with such similar characteristics allows for a direct comparison of their behavior under the influence of the Sun, something that has never been possible in this way before. Each new measurement provides essential pieces for understanding how these bodies form, evolve, and travel through the galaxy, and how this material might be related to planetary formation processes around other stars. As the monitoring of B1 progressed, astronomers began to notice an aspect that surprised even those who have spent decades studying comets. The way the object reacted to the gradual increase in solar radiation seemed to reproduce patterns already known from 3I Atlas, but with an intensity that varied in a controlled and predictable manner. This is important because interstellar comets often exhibit unexpected behavior due to the lack of a thermal history in our system. When an object that has spent millions of years in extremely cold regions approaches the Sun for the first time, it is not uncommon for it to exhibit sudden bursts of activity or the release of unstable compounds. In the case of B1, the release of gas and dust occurred gradually, a sign that its nucleus might have a more cohesive or less fractured structure than that of 3I Atlas, whose activity has been characterized by abrupt and sudden changes. The detailed study of the variation in its brightness allowed researchers to estimate the rate at which the ice sublimated, as well as the proportion of particles released. This measurement is crucial because it helps determine the type of materials present on the surface and inside the nucleus. The data indicated that B1 contained a mixture of volatile compounds that matched those detected in 3I Atlas, but in smaller proportions, which could mean that B1 is a smaller object or that it has undergone less internal alteration during its journey. Analyzing these emissions revealed that certain ionization patterns followed a curve similar to that recorded in 3I Atlas, especially at wavelengths associated with diatomic carbon. This spectral match generated particular interest because it could prove key to identifying whether both objects originated from chemically compatible regions outside the solar system. As these studies progressed, an important question arose. If B1 was indeed an interstellar comet, what would its point of origin be? To try to answer this question, astronomers traced its reverse trajectory, mathematically retracing its path through time using advanced dynamical models. This method allows them to visualize the path the object might have taken before entering the system. Although uncertainties are large, due to the small gravitational variations that can affect the trajectory of any body, initial results indicated that B1 came from a region of space far from the galactic plane, which is consistent with what has been observed in some previous interstellar objects. This coincidence further strengthened the idea that B1 is not a local body, but a visitor that could have been ejected from a distant star system millions of years ago. Another element that drew attention was the way B1 interacted with the solar wind. Conventional comets usually exhibit predictable behavior as the wind pulls the iron tail away from the Sun. In the case of B1, although its tail was shorter and less bright than that of 3I Atlas, it followed very similar patterns in terms of orientation and dispersion. This similarity not only reinforces its classification as an active comet, but also allows for a direct comparison of the electromagnetic forces acting on both objects. Analyzing these interactions is fundamental to understanding the tail's structure and identifying the types of ionized molecules that the Sun excites during the process. In the case of BUE1, small bursts of particles were detected that appeared to respond to variations in the solar wind. These signals are consistent with those observed in comets with more fragile internal structures or higher concentrations of trapped gases. One of the most complex parts of the analysis focused on the density and estimated size of the nucleus. Determining the exact size of a comet is one of the biggest challenges in cometary astronomy, as the brightness of the coma can completely obscure the nucleus. However, using modeling techniques based on light scattering, the researchers concluded that BUE1 likely has a small nucleus. Perhaps smaller than that of 3I Atlas, although this could suggest a lower capacity for activity, the presence of volatile compounds confirms that it is stable enough to form an observable coma. This balance between size and activity is of interest because it may indicate that B1 comes from a region of space where cometary formation processes differ slightly from those that produced similar objects. While these models were being completed, attention turned to the possible rotation of the nucleus. Periodic variations in brightness were detected in 3I Atlas, revealing that its nucleus is rotating at a relatively rapid rate. For B1, although the changes were less obvious, slight fluctuations were identified that suggested the presence of moderate rotation. Rotation can directly influence the type of activity observed, since areas exposed to the Sun for longer periods tend to release more material. In B1, these areas appeared to become more active as the days progressed, generating a pattern of activity that coincided with small changes in the object's orientation. This finding is also significant because it allows for a comparison of the internal mechanics of two interstellar comets under similar conditions. Based on this data, several research groups began working on models to explain why the two objects exhibit such striking similarities. Although it cannot be stated with absolute certainty that they originated from the same environment, the parallels in composition, behavior, and orbital dynamics are too remarkable to be considered a simple coincidence. One possibility is that both emerged from a stellar system where the primordial materials contain particular proportions of carbon ice and organic compounds. Another possibility is that both were the result of similar ejection processes, such as intense gravitational interactions with massive planets or companion stars. Each new observation added another piece to this puzzle, reinforcing the idea that B1 and 3I Atlas represent a rare opportunity to study not only objects crossing our system, but real fragments of galactic history. The simultaneous presence of both objects also opened the possibility of directly comparing their response to the solar environment. As B1 ventured deeper into the system, its brightness gradually increased, and small modifications in the shape of its coma became more evident. This provided valuable information about the inner layers of the core, since more volatile materials tend to sublimate before more resistant ones. This sequence of compound release is particularly interesting because it allows the reconstruction of the object's thermal history. In the case of 3I Atlas, abrupt changes in its activity have been interpreted as signs of internal fractures or the sudden release of trapped materials. In B1, the activity appeared more moderate and controlled, which could indicate a less disturbed nucleus. The combination of these elements further solidified the importance of the discovery of W1, as it provided a perfect basis for comparing the behavior of two interstellar comets under the same solar context. The possibility that they shared similar structural or chemical characteristics motivated the scientific community to redouble its efforts, expanding observations to multiple light ranges. This international coordination made it possible to obtain data that would otherwise have been impossible to acquire in such a short time. The combined view of these studies revealed that B1 is not only an interesting object in itself, but also an essential complement to better understanding the behavior of 3I and Atlas I, and by extension, any interstellar comet that may be detected in the future. As observations progressed, astronomers began to notice that B1 exhibited a particularly interesting evolution in the behavior of its coma. Although it initially appeared to be a diffuse and relatively compact cloud, as the days passed it began to show more defined layers that responded to solar radiation in a manner very similar to what was observed in 3I Atlas. This layered structure is not common in all comets, as it depends on the composition and internal distribution of the ice. In the case of B1, the formation of these layers could indicate that the comet harbors different types of volatile compounds in separate zones, which is consistent with studies of interstellar objects that have preserved very old chemical materials without having been exposed to heat for long periods. One of the most analyzed details was the way the coma's density fluctuated slightly as the object rotated. Although the rotation wasn't yet fully confirmed due to limited data, variations in brightness indicated that certain regions of the core began to sublimate when exposed to sunlight. This pattern resembled that observed at Minden Center, TR Atlas, whose activity also exhibited areas of preferential sublimation. These similarities allowed researchers to make deeper comparisons about the nature of the cores of both objects. The irregular shape of 3 Atlas had already been documented by high-resolution telescopes, leading to the idea that its structure might be composed of tightly bound fragments or an elongated core. In B1, although the shape was still uncertain, the light distribution suggested an irregular surface that also influenced how gas escaped into space. In parallel, spectra obtained with high-precision instruments revealed that B1 emitted traces of complex organic compounds, including light hydrocarbons that have also been detected in local comets. However, the proportion of these compounds did not match that of comets, which are typical of the solar system, further reinforcing its classification as an interstellar object. This peculiar chemical signature attracted attention because it provided valuable clues about the environment where the object may have formed. Planet formation models in the outer regions of star systems suggest that these organic compounds can be preserved for billions of years if they remain in extremely cold environments, far from the heat of the main star. This aligns with the idea that B1 and 3I Atlas could have spent much of their existence in regions where stellar radiation is minimal. As the analyses continued, another aspect that emerged was the relative size of the tail. Although B1's tail was smaller and less luminous than 3I Atlas's, its orientation showed clear signs of interaction with the solar wind. This allowed astronomers to measure the speed at which the ions were being swept away, which is key to understanding the type of materials the comet releases. In view, the speed of these ions matched that of active, but relatively compact, objects. This characteristic reinforced the idea that the comet possessed a small nucleus, but with enough volatile compounds to generate sustained activity. Direct comparison with 3I Atlas, whose tail is more prominent due to its higher level of activity, provided a useful frame of reference for understanding B1's behavior during its approach to the Sun. Another important point of study was the rate of mass loss. To calculate it, astronomers analyzed the amount of dust and gas present in the coma, as well as the speed at which the material was being ejected from the comet. Although the exact rate could not yet be precisely determined, preliminary values showed that B1 was losing mass at a rate consistent with moderately sized comets from cold regions. This data is crucial for estimating the object's lifespan, since very small comets can lose much of their volatile material in a short period. However, B1 showed sufficient stability to remain active for an extended period, allowing observatories to schedule a series of long-term observation campaigns. While these calculations were being performed, another interesting factor emerged: the possibility that B1 had a layered internal structure. This hypothesis was based on the way certain compounds appeared to be released sequentially as the object approached the Sun. This type of behavior is generally observed in objects that have accumulated layers of ice with different sublimation points. Identifying these patterns is key because it helps reconstruct the object's thermal history and better understand the processes that influenced its original formation. In the case of 3 Atlas, some observations had already suggested the existence of internal layers with different levels of activity, and seeing similar signals led scientists to seriously consider the possibility that both objects could have formed in regions of the same stellar system with similar environmental conditions. Throughout these investigations, the scientific community began to focus on the possibility of making projections about the future behavior of B1. While the object showed no signs of having a fragile or fragmentation-prone core, interaction with the Sun could generate drastic changes in its structure. In the case of 3I Atlas, incidents have been recorded that suggest possible internal ruptures. V1, although more stable, could experience sudden increases in activity if certain internal layers were to begin sublimating simultaneously. To anticipate these events, simulation models were continuously updated as new observations emerged. The combination of all these elements made B1 an object of enormous scientific interest, not only because of its rarity as an interstellar comet, but also because of the opportunity it presents to compare 2 bodies of external origin under the same solar conditions. The simultaneous analysis of B1 and Atlas 3I provides an unprecedented opportunity to study how 2 interstellar comets with similar properties behave, allowing astronomers to build a clearer picture of the processes occurring in distant regions of the galaxy. This direct comparison is one of the most important achievements of modern astronomy, as it provides information that would be impossible to obtain otherwise. As coordinated observations progressed across different light ranges, B1 began to show variations that helped astronomers better understand the object's physical structure. One of the first conclusions was that B1's activity was not completely uniform across its surface, suggesting that the nucleus has areas with slightly different compositions or regions where ice is more directly exposed. This pattern became evident when analyzing how the brightness intensity fluctuated at regular intervals, indicating that the comet might be undergoing moderate rotation. Although the exact rotation speed could not yet be determined with certainty due to the object's distance, the repetitive fluctuations in the coma showed clear signs that the nucleus was rotating on its own axis. This feature is common in many comets and helps explain why certain regions appear to be intermittently active. As the object continued its approach to the Sun, instruments began recording more pronounced changes in the coma's distribution. Instead of expanding uniformly, some areas seemed to spread more rapidly, suggesting that the comet was releasing material from specific points on its surface. This behavior resembles what was previously observed in 3I Atlas, whose activity featured particularly active regions that propelled jets of gas with greater consistency. In B1, although the level of activity was lower, the patterns were strikingly similar, allowing researchers to begin speculating about the possible presence of internal fractures or natural cavities where ice had accumulated in higher concentrations. These formations may result from processes that occurred during the comet's formation in its parent system, especially if it was exposed to episodes of material accumulation at different stages of its development. In parallel with these findings, the spectra obtained in the ultraviolet range began to show additional characteristics that further reinforced the classification of B1 as an interstellar object. Among the compounds identified were traces of carbon monoxide, an extremely volatile gas that typically sublimates even under extremely cold conditions. The presence of this compound not only indicates the existence of fresh ice inside the comet, but also suggests that B1 has not undergone repeated heating cycles, like comets in our solar system. In local objects, the presence of carbon monoxide tends to decrease over time due to the gradual loss of volatile material. In contrast, in a comet newly arrived from interstellar space, These compounds can be found in large quantities, preserved for millions or even billions of years. Analysis of these emissions allowed for deeper comparisons with 3I Atlas. Data obtained from 3I Atlas showed a significant presence of carbon monoxide, as well as other complex organic compounds. In B1, although the concentration was lower, the signals were clearly present. This similarity in the relative proportions of certain compounds was noteworthy because it could indicate that both objects formed in chemically similar environments. The outer regions of young star systems, where temperatures are extremely low, favor the accumulation of these materials as solid ice. If B1 and 3I Atlas arose in such an environment, they most likely carry with them a chemical composition that directly reflects the primordial environment of their parent system. As the chemical analyses continued, another aspect that began to emerge was the way the comet scattered sunlight. The reflectivity of B1's coma was relatively low, which is consistent with objects containing high levels of dark organic compounds on their surface. This type of material is common in primitive comets and objects that have not been significantly altered by thermal processes. The presence of dark material helps absorb solar radiation and can influence the rate at which the comet releases gas as it heats up. In the case of B1, this moderate absorption seemed to contribute to the gradual behavior that telescopes were recording. Unlike 3I Atlas, whose brightness had shown dramatic increases, B1 appeared to respond in a more controlled manner, possibly due to differences in its internal structure or the distribution of volatile compounds. Another important detail was the analysis of the dust present in the coma. To understand it, astronomers studied how light was scattered as it interacted with the particles. This technique allowed them to estimate the approximate size of the dust released by the comet. In B1, the particles appeared to be relatively small, which is typical of newly activated comets. Small particles are usually ejected more easily due to the pressure of the gas released during ice sublimation. This suggests that the comet was undergoing a gradual activation process, exposing increasingly deeper layers as it traveled along its path. This observation coincides with interstellar objects that have never been near a star and are beginning to release fresh material for the first time. In parallel, dynamic simulations continued attempting to reconstruct the possible point of origin of B1. Although the uncertainty remained high, the models showed that the object had likely spent millions of years traveling through interstellar space before crossing the boundary of the solar system. This prolonged trajectory could have been caused by gravitational interactions with other massive objects, or even by B1's passage near a moving star. The possibility that B1 was ejected from its home system due to this type of interaction reinforced the idea that the dynamic processes affecting comets can occur in any region of the galaxy, not just in the vicinity of the Sun. While astronomers analyzed the trajectory, they also focused on determining the object's future dynamics. Since B1's orbit exhibited hyperbolic characteristics, it was almost certain that the comet would not remain in the solar system once it completed its close approach to the Sun. This pattern is common in at least 200 interstellar objects that typically enter the system at high speed and then exit again without being captured by the Sun's gravity. The fact that B1 followed this pattern further reinforced its classification as an interstellar object and gave observatories a limited window of time to collect data. This urgency prompted several research centers to maximize their observing time to gather as much information as possible before the comet moved too far away. Finally, the simultaneous presence of B1 and 3I Atlas led the scientific community to consider the possibility that we were facing a unique opportunity. The chance to study two interstellar objects with such similar characteristics within the same time frame offered a historic occasion to directly compare their physical, chemical, and dynamic properties. These comparisons will not only help astronomers better understand comet formation processes in other star systems, but could also reveal important clues about how matter is distributed and evolves in interstellar space. Each new observation added another piece to the puzzle, reinforcing the idea that B1 and the 3I Atlas represent a unique opportunity to explore materials that formed far from the Sun and that preserve crucial information about the early stages of distant star systems. As B1 continued moving toward increasingly brighter regions of the solar system, astronomers began to notice significant changes in its activity level. Although there had been signs of ice sublimation from the beginning, it was during this approach phase that the instruments detected a more marked increase in gas production. This increase was not sudden, but rather constant and progressive, a behavior that specialists associated with the presence of internal layers of ice that were beginning to be exposed. This type of evolution is typical in comets that have never been heated by a star, as their internal structure retains volatile materials in their primordial state. The fact that B1 exhibited these characteristics only reinforced its classification as an interstellar object, since comets born within the solar system often undergo repeated cycles of close approaches that alter their surface compositions. Detailed study of the gas flow allowed for more precise estimates of the nucleus's porosity, a key parameter for understanding its internal structure. In Vune, the data indicated that the nucleus material could have a highly porous composition, similar to that of other interstellar objects studied previously. A porous structure facilitates the gradual sublimation of ice because it allows gas to escape through numerous microscopic channels. This behavior coincides with that observed in 3IL, whose nucleus also showed signs of extreme porosity. The similarity between the two cases sparked particular interest in the scientific community, as it suggests that the formation processes of interstellar comets could produce nuclei with similar physical characteristics, regardless of their size or activity level. Once the analyses confirmed the presence of these porosity patterns, the researchers began to study the thermal distribution within B1's nucleus in greater detail. To do this, they used energy transfer models that simulate how the sun's heat penetrates the comet's interior. These models showed that B1's porous structure facilitated heat penetration, accelerating the sublimation of the surface layers. However, they also revealed that the inner layers remained relatively cool, which explained why the increase in activity was so controlled. This process is also consistent with the behavior of 3I Atlas, whose activity has shown stages of gradual variation before exhibiting more pronounced increases. In both cases, the researchers suspect that the internal structure of these objects is composed of layers that formed at different stages of the development of their parent system. While these thermal studies were being completed, another aspect began to gain prominence: the evolution of the coma's color. Although a characteristic greenish glow had been observed since the first records, during this phase of approach to the sun, the color intensity increased slightly. This type of variation is usually due to the increased activity of specific molecules, such as diatomic carbon, which emits green light when excited by solar radiation. These color changes are extremely useful because they serve as direct indicators of the type of material that is sublimating. In Vune, the persistent presence of this emission, a green color matched that recorded in Comet 3 Atlas, reinforcing the idea that both objects might share a surprisingly similar internal chemistry. If this were correct, it would allow astronomers to study two different representations of the same type of interstellar material. At the same time, telescopes equipped with highly sensitive sensors obtained more detailed images, showing how the coma expanded and changed shape as the comet rotated. These images revealed subtle differences in the coma's density, indicating the presence of active regions irregularly distributed across the nucleus's surface. This pattern had also been observed in Comet 3I Atlas, whose activity showed regions with more intense emissions due to the shape of its nucleus. Although there was still no evidence to confirm a similar shape in Comet B1, the variations in the coma's distribution suggested that its nucleus might have a complex geometry, possibly composed of several regions with different levels of heat exposure. As these investigations progressed, some research groups began to analyze possible scenarios for the origin of Comet B1. Although the reconstructed trajectories still had significant margins of error, several models agreed that B1 could have originated from an interstellar region with relatively low star density. These regions often harbor large molecular clouds where young star systems form. If B1 arose in such an environment, its composition may directly reflect the chemical conditions of that environment. These types of regions, characterized by extremely low temperatures, favor the formation of ice and organic compounds that can remain trapped inside comets for millions of years. Interestingly, analyses of B1's composition matched what is expected of an object formed in this type of environment. In particular, the relative abundance of volatile compounds such as carbon monoxide and light hydrocarbons suggested an origin in regions with limited stellar radiation. Comparative studies between B1 and 3I Atlas also began to include assessments of the dust density released by both comets. In B1, the particles appeared to be small and light, which is typical of newly activated comets. In the Atlas 3I instrument, the instruments had detected particles of various sizes, which could be due to its higher level of activity. Comparing the two particle distributions allowed astronomers to obtain more detailed information about the differences in the internal structure of the two objects. This information is essential for understanding why the two comets show different levels of activity despite having similar chemical compositions. Finally, continuous observations of B1 allowed the scientific community to project its future behavior with a moderate level of accuracy. Although the comet continued to exhibit stable and controlled activity, models indicated that it was likely to reach its peak sublimation point as it approached the Sun even closer. This process could reveal internal layers containing even more volatile compounds, allowing astronomers to study materials that have remained frozen since the object's formation. The opportunity to analyze these materials in two distinct interstellar objects represents a historic advance for modern astronomy, offering a completely new perspective on the diversity of comets that exist outside the solar system. With the steady increase in activity at Vune, astronomers took advantage of each new observation window to improve the accuracy of measurements of the coma and tail. One of the most interesting discoveries emerged when instruments began to record subtle changes in the density of the iron tail. Although the tail was shorter than those of highly active comets, its fluctuations appeared to react immediately to variations in the solar wind. This type of rapid response is characteristic of comets with very fine particles and highly ionizable gases, which is consistent with what has been observed in previously studied interstellar objects. The presence of ions in specific proportions, especially at wavelengths associated with carbon molecules, further reinforced the idea that B1 contained chemical material similar to that of Atlas III. This similarity was observed not only in the behavior of the coma, but also in the way the object responded to changes in the solar environment. While these variations in the tail were being analyzed, telescopes equipped with highly sensitive cameras also recorded an increase in dust scattering. The nature of this dust is important because it can reveal the object's thermal history. In local comets, dust tends to show more uniform patterns due to repeated cycles of close approaches to the Sun. In contrast, the dust in B1 showed a more chaotic, yet very fine, scattering, indicating that the released material was fresh and relatively unprocessed. This is entirely consistent with an object that had never before encountered a significant stellar heat source. The presence of fine, highly volatile particles allowed researchers to conclude that B1 was a primordial comet composed of materials that likely formed during the early stages of the star system from which it originated. In parallel with these studies, new models began to emerge attempting to explain the similarities between B1 and comets 3 and Atlas. From a planetary formation perspective, although both objects exhibited different levels of activity, their chemical, spectral, and dynamic behavior suggested they may have formed in regions of the same type of interstellar environment. These regions, characterized by extremely low and high temperatures and densities of simple organic compounds, favor the formation of ice and dust clumps that eventually give rise to comets. If B1 and 3I Atlas formed in similar regions, this would explain why both show spectral emissions dominated by volatile compounds such as diatomic carbon and carbon monoxide. This type of data not only helps us understand their composition, but also offers clues about the chemistry of protoplanetary disks around young stars in different parts of the galaxy. As studies of the dust and gas composition progressed, experts began to examine more closely how solar radiation was affecting the object's internal structure. One of the most important tools for this type of analysis is measuring the heat reflected by the coma. Although the nucleus of comet B1 cannot be directly observed due to its small size, the thermal characteristics of its coma allow scientists to estimate the comet's surface temperature. These measurements indicated that B1 was absorbing more solar energy as it approached the Sun, accelerating the sublimation of its surface ice. However, the temperature increase was relatively moderate due to the object's composition and its possible porous structure. This combination of factors prevented sudden bursts of activity, something that has been observed in comets with more fragile internal structures. B1's controlled behavior allowed astronomers to obtain stable data over longer periods, facilitating the construction of more accurate models. While specialists analyzed the thermal evolution, they also began to study the possible three-dimensional structure of the coma. Using advanced modeling techniques based on light scattering, they were able to recreate how the gas and dust were distributed around the nucleus. These models showed that B1 had a slightly asymmetrical coma, suggesting that its activity did not originate from a completely uniform surface. This irregularity could be due to differences in the internal distribution of volatile compounds or variations in rotation speed. Although the data were still insufficient to confirm a specific structure, the similarities to the patterns observed in 3 Atlas were too clear to ignore. The possibility that both comets shared similar physical characteristics reinforced the idea that they might have formed in regions with similar environmental conditions. Meanwhile, spectral analyses continued to yield intriguing results. One important feature was the presence of certain free radicals in the coma that form only under specific radiation conditions. These radicals are highly sensitive indicators of an object's composition and help determine how the material reacts under conditions of solar excitation. In Vune, The presence of these radicals was consistent with that of primitive comets that have not been affected by repeated heating cycles. In the case of 3I Atlas, measurements had revealed a very similar pattern. This chemical parallel further reinforced the hypothesis that both objects might have a comparable internal composition, opening the door to deeper studies on how interstellar comets form and evolve in different regions of the galaxy. As the analyses continued, several scientific teams began to consider the possibility of detecting deeper structural changes in the nucleus as the object approached its peak activity. Although B1 appeared stable and showed no signs of fragmentation, interstellar comets can react unpredictably to stellar heat due to the presence of highly volatile internal layers. The possibility that B1 might experience a sudden increase in activity motivated researchers to continuously monitor the object. This monitoring revealed slight increases in the intensity of the coma, possibly indicating the beginning of sublimation of deeper internal layers. Although these changes were still small, the comet's steady progression toward warmer regions suggested that further observations could reveal more significant variations over time. B1's evolution during this period became a key point for comparative studies among interstellar comets. While 3I Atlas was going through phases of intense activity, B1 exhibited more moderate, but equally revealing, behavior. The ability to simultaneously study two interstellar objects with different levels of activity is extremely valuable because it offers a broader perspective on the physical processes occurring within these bodies. Each new reading contributed to a clearer picture of the diversity of comets outside our solar system and how they react when they encounter a star's radiation. The accumulating data reinforced the idea that V1 might be a smaller object, with more controlled activity, but equally rich in information about its origin. As the days passed and the comet B1 continued to be monitored, astronomers began to delve even deeper into the physical processes occurring within its nucleus. One of the most important observations arose when high-resolution telescopes detected slight variations in gas emission at different wavelengths. These variations indicated that deeper layers of the nucleus were beginning to heat up, releasing compounds that had previously remained dormant. This type of transition is characteristic of comets composed of primitive ice formed in regions very distant from their parent star. The gradual behavior of the activity reinforced the idea that B1 possessed a highly conserved internal structure, one that had not undergone repeated heating processes like native comets in our solar system. These new emissions allowed astronomers to identify additional molecules that had not been detected in the earlier observations. Among them were traces of carbon dioxide and certain heavy hydrocarbons that are common in young molecular clouds. The presence of these compounds provided further clues about the environment in which B1 may have formed. In many forming star systems, carbon dioxide freezes into dust particles and is only released when the object experiences a significant temperature increase. The fact that B1 began releasing this material just as it entered warmer regions of the solar system was compelling evidence that we are dealing with an extremely old comet that preserves a mixture of volatile compounds dating back to the early stages of its parent system. Meanwhile, observations made in infrared light began to reveal details about the surface temperature of the nucleus. In B1, the temperature increased slowly, indicating that the comet's structure was gradually absorbing solar energy. This behavior is typical of an object with a surface made of or covered by dark dust grains that act as a thermal insulator. In comparison, 3I Atlas showed a more rapid increase in its surface temperature, which could be explained by differences in its internal structure or by the presence of areas more exposed to the sun. This direct comparison revealed that although both objects shared similar chemical characteristics, the way they reacted to the solar environment could be different, probably due to differences in size, internal composition, or thermal history. While these thermal studies were underway, researchers also focused on the evolution of B1's dust tail. Although initially small, its shape began to change as the object approached the sun. Lighter particles were strongly pushed out by solar radiation, while heavier particles remained closer to the core. This difference in dust behavior allowed researchers to estimate the particle's density and approximate size. The data indicated that B1 was primarily releasing very fine dust, suggesting that the comet had a relatively fresh surface, lacking thick layers of processed material. This characteristic distinguished it from some local comets that, after multiple close approaches to the sun, develop a hardened surface crust, as seen in Vune. The absence of this crust further reinforced the idea that the object had never before been so close to a star. In addition to studying the dust distribution, astronomers began analyzing variations in the shape of the coma. As the comet rotated, the shape of the coma changed slightly due to the release of material from specific areas of the nucleus. This type of variation is extremely useful for determining the orientation of the rotation axis and for identifying potential active zones on the surface. In Vune, the data suggested that the rotation axis might be slightly tilted relative to the plane of its trajectory, which would explain why some regions heated up faster than others. This behavior is consistent with observations of 3IL, whose activity also shows preferential zones associated with its shape. Although a direct image of B1's nucleus is still lacking, variations in its coma provided enough information to begin building models of its three-dimensional structure. As these studies progressed, another aspect began to gain relevance: the comet's stability. Many interstellar objects exhibit unpredictable behavior when heated, which can lead to sudden bursts of activity or even internal fractures. In the case of B1, initial models suggested that the nucleus was relatively stable and showed no signs of imminent fragmentation. However, astronomers continued to carefully monitor any sudden increases in brightness or abrupt changes in the direction of the gas jet. B1's stability contrasted sharply with that of 3I Atlas, which had already displayed episodes of intense activity. This difference allowed scientists to compare how two interstellar comets react to solar heat in distinct ways, providing a broader view of the possible types of nuclei that exist in interstellar space. In parallel, teams specializing in orbital dynamics began to project B1's future trajectory with greater precision. The most recent measurements confirmed that the comet was following a hyperbolic orbit, which means it will not remain in the solar system once it completes its close approach to the Sun. Most likely, after passing through perihelion B1, it will re-enter interstellar space. Continuing its journey for millions of years, this trajectory is entirely consistent with what is expected of an interstellar object, since its speed and angle of entry into the solar system prevent it from being captured by the Sun's gravity. The confirmation of this trajectory reinforced the importance of obtaining as much data as possible within the limited time available. As the scientific community analyzed these findings, a general consensus emerged. Comet B1 represented an invaluable opportunity to understand processes that until very recently were completely inaccessible to astronomy. The fact that B1 shared so many characteristics with 3I Atlas allowed for unique comparisons between two real interstellar objects, something that had never been possible before. Each new observation provided details that helped reconstruct the origin, evolution, and behavior of these space travelers that transport materials formed in remote regions of the galaxy. The discovery of B1 not only doubled the amount of data available on interstellar objects, but also significantly expanded our understanding of the diversity of materials and processes that can occur beyond the solar system. As research on Vune progressed, astronomers began to focus on an aspect that became central to understanding the object's deep nature: its thermal response as it moved toward brighter regions of the solar system. Studying temperature is fundamental because it allows scientists to determine not only the rate of ice sublimation, but also the finer characteristics of the material that makes up the nucleus. In the case of B1, measurements revealed a particularly interesting behavior. Although the surface temperature gradually increased, the nucleus remained relatively cool, even cooler than expected for a newly activated comet. This discrepancy indicates that B1's internal material possesses a significant level of thermal insulation, likely due to a highly porous structure that acts as a heat barrier. This pattern is consistent with observations in other interstellar comets and suggests that B1 has preserved a nearly intact internal structure for millions of years. As studies on temperature progressed, researchers began to identify differences in how various molecules were released from the nucleus. In particular, carbon dioxide and complex organic compounds showed a gradual release that increased in phases, which is typical of an object containing internal layers of more volatile material. Comets in the solar system, due to their multiple close approaches to the Sun, usually lose these internal layers and develop more homogeneous structures over time. In contrast, B1 showed a clearly stratified structure. This characteristic of bodies formed in interstellar regions, where extreme cold preserves the original mixture of ice and dust almost intact, places the comet in a special category, as it offers a direct window into processes that occurred in the early moments of its system of origin. As chemical studies deepened, another aspect began to gain prominence: the object's interaction with the solar wind. Observations at specific wavelengths showed that B1 responded immediately, even to slight variations in the density of the solar wind. This reaction was observed as small increases in the coma, which appeared to expand briefly when certain bursts reached the object. The comet's sensitivity to these variations indicates that activity on its surface was dynamic enough to reflect environmental changes almost in real time. This type of behavior has also been documented in Atlas 3I, whose coma shows fluctuations associated with solar wind conditions. The similarity between the two objects reinforces the idea that interstellar comets may share consistent physical properties, regardless of their differences in size and activity level. As these observations progressed, experts began to study the radiation scattered by the comet's tail in greater detail. The dust tail, although relatively small, showed interesting patterns that helped determine the size distribution of the ejected particles. Analyses indicated that most of the dust was extremely small, which is typical of comets experiencing their first significant exposure to a star's heat. In view, this presence of fine dust suggested that the surface layers of the nucleus had not yet been disturbed by previous heating processes. The absence of large particles indicates that the core material might be fragile, but at the same time very primitive. This finding also coincides with what was observed in 3 Atlas, where smaller particles dominated the early stages of activity. As research on the tail progressed, broader questions arose about the possible composition of the comet's interior. Although telescopes cannot directly observe the nucleus of such a small and distant object, spectral measurements allow scientists to accurately infer what kind of material might be found in the deeper layers. In the case of B1, the data suggested the presence of more complex organic compounds, possibly resulting from chemical interactions that occurred in a dense molecular cloud before the comet formed. These compounds have also been observed in other interstellar objects studied in recent decades, suggesting that complex organic chemistry might be common in star-forming regions. This coincidence not only reinforces the importance of studying B1, but also suggests that the materials it carries could be representative of chemical processes present in different regions of the galaxy. As the chemical and thermal analyses continued, another point began to gain relevance among the researchers: the possibility that B1 might undergo significant structural changes as it approached the Sun was a concern. Although the comet had shown stability up to that point, models indicated that the sublimation of internal layers could weaken certain regions of the nucleus. In some interstellar comets, this process has led to partial fragmentation or even complete breakups, although there were no clear signs that B1 was at immediate risk of fragmentation. Experts maintained constant monitoring to detect any changes in the shape of the coma, as this type of alteration is often the first indication of a significant structural change. B1's stability contrasted sharply with that of 3I Atlas, which had already shown episodes of intense activity. This difference allowed researchers to compare 2 completely distinct behaviors in interstellar comets exposed to solar heat. As observations progressed, some teams began to study the interaction between the comet's activity and solar V radiation. This relationship is especially important because V radiation can decompose certain molecules and generate radicals that only form under specific conditions. In view, the presence of these radicals was consistent with what has been observed in comets containing extremely old material. The detection of free radicals provided further evidence that the comet was composed of compounds that had remained unaltered since its formation. Combined with data from 3I and Atlas, this observation allowed researchers to construct a broader picture of the atmospheric chemistry of interstellar comets. As these studies progressed, one point became particularly relevant: the importance of comet B1 as a scientific tool. The near-simultaneous appearance of B1 and 3I Atlas allowed for real-time comparison of the activity of 2 interstellar objects with similar compositions and behaviors. This temporal coincidence is extremely rare and provided astronomers with a historic opportunity to study processes that are not normally observable with such clarity. The ability to compare 2 interstellar objects under the same solar conditions opened up an entirely new line of inquiry that could transform our modern understanding of the diversity and evolution of comets in the galaxy. With the steady progress of observations dedicated to B1, astronomers began to consolidate a much clearer and more complete view of the object's scientific relevance, especially in comparison with what had already been learned about 3 Atlas. One of the most important conclusions that emerged in this final phase of the analysis was that B1, despite having a more moderate level of activity than 3 Atlas, represented an extraordinarily pure example of an interstellar comet. It was possibly even more pristine in certain aspects. This was due to the way its activity developed gradually, without the abrupt changes that usually signal internal fractures or sudden material release events. Its controlled behavior allowed for more stable measurements, providing exceptionally high-quality data on the sublimation rate, the types of compounds released, and how these interacted with solar radiation. One of the most significant findings in this final phase was the detection of thermal signals from deeper regions of the nucleus. Although most of the heat remained in the surface layers, reflecting the object's insulating structure, some thermal waves reached internal areas and triggered the gradual release of compounds that had been trapped since the comet's formation. This transition allowed astronomers to identify molecules that are not usually easily detected in the early stages of activity. Among these compounds were some complex hydrocarbons whose presence is directly related to extremely cold formation environments, typical of dense molecular clouds. This chemical signature reinforced the idea that B1 was an exceptional representative of the processes occurring in remote regions of the galaxy, where young star systems are born. As the chemical studies progressed, it also became clear that the comet's activity was undergoing an evolutionary pattern closely linked to the rotation of its nucleus. The variations in brightness, which had previously appeared random, now showed a clearer periodicity as the object released gas from specific regions of its surface. Although scientists could not yet state with absolute certainty the exact rotation period, the recorded variations suggested that B1 might be rotating at a moderate rate. This behavior is important because it provides indirect information about the internal stability of the nucleus. An object that rotates too rapidly risks fragmenting if its structure is fragile. But B1 appeared to maintain a stable equilibrium between its rotation speed and the internal cohesion of its material. This stability allowed the comet to remain intact, even as it approached regions where solar radiation was considerably more intense. As the comet's activity increased, changes in the tail's structure also began to be observed. Although this tail remained shorter and less bright than that of 3I Atlas, its evolution provided important clues about the properties of the released dust. In particular, analyses showed that the average particle size remained extremely small. This implies that B1 was still releasing fresh material from internal layers that had never before been exposed to heat. This characteristic is key to understanding the comet's history, as it demonstrates that its internal structure retains virtually intact the chemical conditions of its original environment. For astronomers, this represents a unique opportunity to study materials that could be the same as, or very similar to, those present in the interstellar medium in remote epochs, before the system from which B1 originated reached maturity. As this data accumulated, the dynamical models used by astronomers began to project the comet's future trajectory with greater accuracy. Everything indicated that once it completed its approach to the Sun, B1 would resume its journey into interstellar space without being captured by the Sun's gravity. This characteristic, typical of hyperbolic orbits, definitively confirmed its interstellar origin. More importantly, the models suggested that B1 would maintain a sufficiently high speed to leave the solar system without experiencing a significant decrease in its orbital energy. In practical terms, this means the comet will continue its journey through the galaxy, possibly without passing near another star for millions of years. This type of trajectory highlights the extreme rarity of the event that astronomers had the opportunity to study. Two interstellar comets detected in the same historical period, both accessible to detailed observations from multiple locations around the world. The simultaneous presence of these two objects also allowed scientists to study how different levels of activity can arise in comets that, despite having formed in similar environments, experience distinct thermal and dynamic histories. While 3 Atlas showed episodes of intense activity, abrupt increases in brightness, and signs of possible fragmentation, B1 maintained more controlled behavior, suggesting that its internal structure may have remained in a more cohesive state throughout its history. This comparison between the two objects provides an extraordinarily valuable perspective on the diversity of structures that can exist among interstellar comets. It not only reveals how the internal physics of these bodies influences their behavior, but also offers fundamental clues about the processes that govern their formation and evolution in environments completely beyond the reach of human space missions. In the final phase of the analysis, astronomers began to consolidate the most important findings that emerged from observations of comet B1. Among these discoveries, one of the most significant findings was the confirmation that the object contained a mixture of materials that faithfully represented the chemistry of the environment where it formed. This mixture included volatile compounds, extremely small dust particles, and organic molecules that only form under specific conditions within dense molecular clouds. The presence of these compounds not only confirmed the comet's interstellar origin, but also provided crucial information about the distribution of materials in regions of the galaxy that cannot be studied directly. B1, like Tri-Atlas, became a kind of cosmic messenger, carrying information about processes that occurred at vast distances from the solar system. As the observation period drew to a close, an idea began to take shape within the scientific community. The consecutive appearance of 2 interstellar comets with such similar characteristics was not just a stroke of luck, but a unique opportunity to substantially expand human knowledge about the matter that exists in the most remote regions of space. The fact that B1 exhibited such a pristine structure and stable behavior made it a crucial reference point for comparison with Atlas III, allowing astronomers to establish connections that would otherwise have been impossible to identify. The simultaneous study opened a new window into understanding how interstellar objects form, evolve, and travel through the galaxy, making it one of the most important scientific events of recent years. The simultaneous study opened a new window into understanding how interstellar objects form, evolve, and travel through the galaxy, making it one of the most important scientific events of recent years. Their simultaneous study opened a new window into understanding how interstellar objects form, evolve, and travel through the galaxy, making it one of the most important scientific events of recent years.